Hello, and welcome back to Unconventional Computing, CS492A in fall 2024. We've started talking about quantum computing, which arguably is also part of unconventional computing because, well, it is still not part of mainstream computing for sure. I've started talking about the quantum mechanics as a foundation, the physical foundation and motivation behind quantum computing as conceived or proposed actually by Richard Feynman in the 70s. And the actual harnessing quantum computing is due to Peter Shor, but that's where we're heading for in this chapter 4. But first, let's recall the axioms of quantum mechanics as introduced by John von Neumann. So let me start the screen sharing. Yes, here we are. And before we recall the axioms of quantum mechanics, let's recall the axioms of Newtonian mechanics as an example of a general theory, physical theory. Any physical theory boils down to a translation between physical objects and their properties on the one hand, and their mathematical descriptions. Mathematics is the language of physics, and we have a kind of translation, a dictionary, and different physical theories amount to different translation, different dictionaries. And it's pedagogically good to start with a simple example, named the simple example of Newton mechanics. So in Newton mechanics, we have, on the one hand, there's physics, and on the other hand, there's mathematics. And how do we translate between these in the case of Newton mechanics? Well, the physical objects we're considering and the properties we're considering will be illustrated at the example of a solar system as described by Newton mechanics. And the objects we describe are systems, isolated systems. If we have a non-isolated system, we need to proceed to a larger system that includes all the interactions. And this is an approximation. So in good approximation, the solar system is isolated. We're going to ignore the effects of galaxy and other forces in good approximation. In Newton mechanics, these are described by phase space, which is a Euclidean space, real numbers raised to the 6 times p, the number of planets, and 6 because we have 3 spatial dimensions, and we have 3 momentum, velocity dimensions for each planet. Next, physical objects are the observables. What are we going to observe about the solar system? We're going to observe, as illustrated here with these eyes, the positions of each planet and the velocity or momentum of each planet, provided that we know the mass of each planet. This corresponds mathematically to projections from phase space. So, for example, if we want to know the x-coordinate of Mars, then that corresponds to a projection from the positions and momentum of all planets to the x-coordinate position of Mars. If we want to observe the y-coordinate of Mars, that's a different projection. If we want to observe the x-coordinate of Earth, that's a different projection. So different observables correspond to different objections but all projections live on the same space, namely the phase space. Next, objects, we will consider states. The state of the solar system is a description of all its constituents, and in Newton mechanics, state of the solar system is completely described by knowing the positions and the velocities of all its planets. So this is kind of, Maxwell's demon. And mathematically, this corresponds to vectors in the state space. Next, about measurement. Performing a measurement means we want to know the value of some observable. We want to know the x-coordinate of Mars. We want to know the velocity of y velocity of Earth. And mathematically, this corresponds to evaluating a projection and observable. So a value of an observable on a state space, that's a result of a measurement. And this looks overly formal, and it is, but the purpose of presenting Newton mechanics in this overly formal way is to demonstrate or to emphasize how quantum mechanics differs from that. So, for example, performing a measurement on the solar system does not change the state of the solar system. Evaluating a projection on some vector capturing the state does not change the vector, does not change the state, which seems so obvious, but as I'm going to turn out, this is not true for quantum mechanics. Just a second here. Next physical property we want to discuss is the evolution. How does the solar system change over time? How does its state change over time? And physically, this means that we have a evolution of state from the initial time 0 to the time t. And mathematically, this evolution is exactly what is described by the Newton laws of gravitation or by the Newton equations. And I'm not going to spell them out because that's not the purpose of today's lecture. But this illustrates how to formalize a very simple and well-known physical theory of Newton mechanics. And now we can see how quantum mechanics differs from Newton mechanics. So in quantum mechanics, a system is described according to John von Neumann and this famous book, Mathematical Foundations of Quantum Mechanics. A system is described not by a Euclidean space, but by a Hilbert space. So here's again an example of an atom, let's say, and this is a quantum object, and it's described not by Euclidean space, but by a Hilbert space. Can be finite dimensional or infinite dimensional. And observable, according to von Neumann in quantum mechanics, is not described by a projection, but by a Hermitian operator. Hermitian basically means symmetric, generalized to the infinite dimensional case. In the finite dimensional case, for a matrix, it means it's symmetric and yes, so self-adjoint operator. And in the complex setting, it means if you conjugate all entries and then perform symmetry reflection on the diagonal, then it remains the same. So that's Hermitian operator. How about states? So state in quantum mechanics are So these are two different states of the atom, and mathematically this corresponds to two different normal vectors in the Hilbert space. Normal meaning they have length 1 in the Hilbert space. And here come one of the essential differences between classical and quantum mechanics. A measurement in quantum mechanics changes the state of the system. So performing a measurement, the result of the measurement will be an eigenvalue of this operator. That's another important difference to classical mechanics, because this operator will have, in general, many eigenvalues, perhaps even infinitely many, and quantum mechanics does not predict which eigenvalue will be the result of the measurement. So there's some kind of non-determinism or randomness inherent to quantum mechanics. And that's one of the reasons why Einstein rejected quantum mechanics. We will return to that later when we discuss the EPR experiment, thought experiment. And finally, the time evolution in quantum mechanics is described by Schrödinger's equation. So this is a partial differential equation or an ordinary differential equation on the Hilbert space, driven by the so-called Hamilton operator, where the Hamilton operator is the Hermitian operator corresponding to the observable called energy. Right? So here, Hilbert Schrödinger equation with a Hamilton operator. Hamilton operator is a Hermitian operator which arises from the physical observable of energy, and that's driving the evolution of a quantum system. So let's spell out these translations more precisely in terms of 5 axioms numbered 1 to 5, following the presentation by John von Neumann. So axioms of quantum mechanics. Axiom 1, remember the correspondence between an isolated physical system and a complex Hilbert space called the state space, finite or infinite dimensional. Then there's an amendment to this first axiom that says if we have a physical system that is composed from mutually connected subsystems, then the state space, the Hilbert space, is the tensor product of the state spaces associated with each component. So what I want to emphasize here, it's the tensor product, not the Cartesian product. That's something we will elaborate later. Okay, that's the first axiom. Second axiom is about states. It says a pure state of the system at time t corresponds to a normal vector, a unit vector in this Hilbert space. And there's also an amendment. This is first part is about pure states, and the second part is about mixed states. Mixed states mean basically statistical ensemble, a mix of pure states in different states corresponding to different normal vectors. And if they occur with real weights between 0 and 1 in this mix, then this mixed state is described by a so-called density operator. Density means positive, semi-definite, trace class 1 operator described here. And here you see also nicely illustrated this bra and ket notation. This is basically a projection, right? So you apply this psi k to some other vector, and then the result will be a real number, a complex number. And this is going to be scaled with the vector psi k, and then also scaled with a weight. And you can do the math and calculate that this is indeed a density operator, positive, finite trace class 1 operator. This is, by the way, this is one of the main motivations for functional analysis course in mathematics, which I strongly recommend to you. Okay, so that's the second axiom. And now we proceed to the third axiom. Remember, third axiom was about the correspondence between physical observables and their mathematical counterpart being Hermitian operator, that is self-adjoint operators in the infinite dimensional case. Right. And yeah, there's an amendment that I also need to emphasize. A measurement of an observable, right, produces some eigenvalue of this operator. Remember that? We'll return to that later. So this is written on the bottom of the slide so that we can keep it in mind and return to it later. For now, we proceed from third to the fourth axiom. Fourth axiom, part A, when the system is in a pure state, then the measurement produces the eigenvalue A, as indicated here, with the probability. So among the many eigenvalues, the different eigenvalues occur with a probability, non-deterministic, intrinsic randomness, where psi A is any unit eigenvector to the eigenvalue A. Now, the mathematicians among you will notice that what if this is a double or degenerate eigenvalue? Then there's not just one possible eigenvalues, but several one. Then there's an axiom which covers that as well, but its formulation is a little bit more complex. So we're going to skip over that case and only consider the case of non-degenerate eigenvalues. So provided that A is a non-degenerate eigenvalue and is discrete, in the infinite dimensional cases, it could also be a non-discrete spectrum. When this is not the case, when A is degenerate or part of the continuous spectrum, then the formula becomes more complicated. It goes beyond the purpose of today's lecture. So that's the first part of axiom 4. The second part of axiom 4 says that after this measurement, the system will be a new state. Remember, I emphasized that in quantum mechanics, performing a measurement is inevitably going to affect the state, which is very different from Newton mechanics, where observing the position of some planet certainly does not change the planet at all, its state. But in quantum mechanics, this is inevitable, as illustrated in the Schrödinger's cat thought experiment, which I'm going to remind you of in a few minutes. So that's a second part of axiom 4a. Actually, axiom 4 has another part, namely when the system is not in a pure state, but in a mixed state. Then we also have two axioms. Axiom 4b, when the system is in a mixed state, remember mixed state is described by a density operator, then measuring the observable A, again produces an eigenvalue A of the operator, but now the probability is given by this formula. And I leave it as an exercise for you to confirm that when the system is in a pure state, which is a special kind of mixed state, then this formula boils down to the above formula. So actually, axiom 4b is more general. It includes axiom 4a, but also it's more complicated. So it's good to state both. Now we need a counterpart to this axiom 4a prime after measurement in a mixed state. After measurement, so this is to remind you of the definition of a density operator. And after measurement of a mixed state, the system will be again in a mixed state. And this is the n-density operator of the system after measurement. So again, performing a measurement affects the state of the system in this way. And again, mathematical exercise, verify that this is again a density operator, again, that is positive semi-definite trace class 1 operator. That's mathematical exercise in functional analysis. Okay, so now we're almost done. Already 4 axioms. Remember, the 5th axiom is the one about the evolution according to Schrödinger's equation. So let's keep in mind the 3rd and 4th axiom and the 2nd axiom, and then stay the 5th axiom only for the case of a pure state evolution. There's a counterpart for the evolution of a mixed state, but we won't delve into that today. So the evolution of a pure state at time 0, psi unit vector, to another unit vector at time t in the same Hilbert space is described by Schrödinger's equation. And here you see again Schrödinger's equation, differential equation with respect to time t of the vector, Hamilton operator applied to this vector at time t. So this is, if you like, this is an ordinary differential equation living in a Hilbert space, where the Hamilton operator is the operator coming from the observable energy according to axiom number 3. Okay, so this is about the axioms, and all we started justifying these axioms and also giving examples of applications of these axioms. So we recalled, why do we, does quantum mechanics require or suggest that a physical system is described by Hilbert space? This is by observing one of the 2 main examples that we discussed for quantum systems, for this schizophrenic duality between particle on the one hand and wave on the other hand, which is experimentally exhibited by light, which is also experimentally exhibited, for example, by electrons. So light can come in different polarization states. And this is described by a 2-dimensional complex Hilbert space, which is just complex numbers squared, Cartesian product. And so we can have light polarized in X direction, or we can have light polarized in Y direction. Why do we need all the other unit vectors in between? Because light can also be polarized diagonally, right? And this is maybe photographers will know that very well. They use polarization filters to enhance the contrast in some pictures involving reflections. So if we have a polarization filter in Y direction, and then another polarization filter in Y direction, then the second one doesn't really have any impact. The light is already polarized in Y direction, thus simply passes through the second polarization filter, whereas when the second polarization filter is oriented in X direction, then no light passes through it because the incoming light is polarized in Y direction and cannot pass through the X polarization filter. But if we have another polarization filter in diagonal direction, like here, then roughly half, or 1/√2 of the original light actually passes through that, which is classically strange because this is polarized in Y direction and not in diagonal direction. But quantum mechanics explains why still part of this light passes through this. And if you place several polarization filters, so one here is in let's say Y direction, the middle one. This one is in X direction. so no light passes through both of them. This is a diagonal polarization filter, so part of the light passes through both the diagonal and the Y polarization filter. This is described or explained by quantum mechanics in this way. And you can perform this also on a larger scale with microwaves, where the wavelength is much larger, and therefore the polarization filters amount to such grades. And if you place two grades orthogonal to each other, then no microwave can pass through it. And this is used in actual microwave ovens to prevent microwaves from leaking through it. So you can look inside, because looking involves light with a small wavelength, but the microwaves have larger wavelengths and therefore cannot pass through two polarization filters oriented orthogonally to each other. But when one is oriented diagonal to each other, then still part of the microwaves can pass through it. This is a well-known and a good experiment. So now let's reconsider this experiment where no light can pass through the second polarization filter. If we insert a third polarization filter, diagonal one, between the two ones, then suddenly light comes through all three of them. And this is called Malus law, because the second polarization filter, diagonal one, part of the light passes through that. And then the third one is oriented diagonally relative to the second one. So again, part of the light passes through the third one. So inserting another polarization filter actually enables light to pass through the two filters. And this is illustration how measurement affects the state of a quantum system, changes the state. Performing an additional measurement changes the polarization of the light, so that now light suddenly passes through the third one. So this is justification and explanation and illustration of the axioms of quantum mechanics. Now let's also illustrate the difference between pure and mixed states. So here we've always talked about pure states, vertically or horizontally or diagonally polarized light. It's all in a pure state. There's other type of pure states of light, that's circular polarized light. Okay, so quantum mechanically, this corresponds to, in this two-dimensional Hilbert space, to orthogonal bases. 0, 1 corresponds to, let's say, Y polarization. 1, 0 corresponds to horizontal polarization. And 1, 1 corresponds to diagonal polarization, but we need to renormalize. 1, 1 is not a unit vector, so 1, 1 divided by square root of 2 is a unit vector. And for later, using quantum computing qubit, this is commonly abbreviated with a boldface 0, and this unit vector is commonly abbreviated with a boldface 1. So this is a different one than this one. This is a symbol explained later. But I already mentioned circular polarized light as another example of a pure state of a light. So here you see diagonal polarized light. Diagonal polarized light is described by 1, 1 scaled with square root of 2 to make it a normal vector. And 1, 1 is just this unit vector plus this unit vector. Or we can also have 0, -1. This is going to be the other diagonal orientation. But these are still linearly polarized. Here's an example of circular polarized light, where the direction of the polarization changes over time. It can change, like in this example, it is, let's see, this is counterclockwise, or it can change counterclockwise, clockwise, and this corresponds to also linear combination of the basis vectors with a complex weight. So here we have weight 1, which is a real number. Here we have weight I, the complex unity, and plus I corresponds to counterclockwise circular polarization, and minus I corresponds to clockwise circular polarization. So this is explains why we deal with a complex Hilbert space, not with a real Hilbert space, because we need these complex weights to describe also this space. So here in our picture previously, we had this is the kind of two-dimensional real Hilbert space, namely the Euclidean plane. But actually, we need to talk about the complex two-dimensional Hilbert space, which is hard to imagine because it's four-dimensional real space. Our brain is not well suited to imagine four-dimensional space. It's good with three-dimensional space, but there's this nice description, so-called Hopf vibration, as a way of imagining four-dimensional unit sphere, not the four-dimensional space, but the four-dimensional unit sphere, embedded in some smart way into three-dimensional space. So you see, this is supposed to be a sphere, but in four-dimensional space, and so there it's kind of filling up three-dimensional ball in a smart way. Right, so plus I or minus I as scalar vector corresponds to clockwise or counterclockwise polarization, but this is still pure state. What about mixed state? Mixed state is actually what arises mostly in light coming from the sun, for example, or from a light bulb. This is a mixed state because there's no special polarization of either kind. It can be considered as a mix of different polarizations. And so incoming is unpolarized light. And then after applying a filter, measurement, the measurement changes the state, and the result will be a pure state, polarized in this type, in this example, in X direction. So difference between pure and mixed states illustrated at the example of light. So now let's look at another example of two-dimensional Hilbert space realized in physics, namely this time using particles, well, more precisely using silver atoms. So this is progressing towards quantum computing. So remember, this is one way of realizing a qubit with polarized light, and another way of realizing a qubit is using a silver atom and using from harnessing its property of having a spin. Spin is a quantum mechanical property that has no counterpart in classical mechanics. It's called spin because it has some resemblance with a ball spinning around its axis, but that's not good. That's not a perfect explanation. Spin behaves differently, and yeah. So let's recall the famous Stirling-Gerlach experiment, where silver atoms are come out of a oven in everything happens in vacuum, and then they are subjected to a inhomogeneous magnetic field. So here you see the North Pole is very strong, whereas the South Pole is is the South Pole is distributed, so the magnetic lines are much more stronger towards this end, and here they are distributed, and this results in the silver atoms moving up or down in this magnetic field, depending on their spin, which interacts with the magnetic field. And classically, this is number 4, one would expect that all possible values for spin can occur, but experiment shows that only 2 possible values occur, spin up and spin down, and nothing in between. So that's another illustration of realizing a qubit with a spin having only 2 possible values in this direction. Of course, we can also orient the magnetic field in, so here it's in y direction. We can do the same in x direction, and then the same happens here with the screen kind of like turned, and we can do it in diagonally. We can all do the same experiments as with light polarization, but now with silver atoms in an inhomogeneous magnetic field. And this is one way of realizing qubit, another way of realizing qubits. So here you see such an example. Here you see 6 qubits realized with spins. Now, technically, this is not silver atoms anymore, but these are magnesium ions in a planar ion trap. And here you see 12 of them, and you see that they are already interacting with each other, forcing each other to this zigzag location. And this is an illustration of this second part of axiom 1, namely if we have several systems that are composed from subsystems, then the state space of that is the tensor product. So here we have 1 qubit, 1 qubit. We have 6 qubits, and the state space of this is the tensor product of 6 two-dimensional complex Hilbert space, which is, what's the dimension of that? Well, if we had a Cartesian product, then the dimensions would add. So 6 times two-dimensional Hilbert space would be a 12-dimensional Hilbert space if it were the Cartesian product. But here it's the tensor product, and the dimension of the tensor product means that the dimensions multiply. So we have 2 to the 6, not 2 times 6 as dimension, but 2 to the 6 is the dimension of the state space of this, which is already 64. So that's a very high dimensional, still finite, but very high dimensional. And the state space of this system would be 2 to the 12. So that's 4,000 dimensional. So we see already the importance that what this is a tensor space, a tensor product, not a Cartesian product, has huge impact. And this has recently been confirmed experimentally that really the state space dimensions grow exponentially with the number of particles. And that's one of the essences of quantum computing, harnessing that exponential large state space dimension. We'll return to that when we discuss Shor's algorithm. So this is not a Cartesian product. In case of Cartesian product, the dimensions would add 6 times 2, 12 times 2, but it's tensor product, which makes the dimension multiply 2 to the 6, 2 to the 12, 64 or 4,000. Okay. And the reason why this is posed as an axiom is because they are so-called entangled spaces. Right? So this has been predicted by these axioms by John von Neumann, and it has been confirmed with entanglement measurements. And one particular such measurement, such experiment is Bell's inequality, measuring Bell's inequality as a consequence of quantum entanglement as a experimental confirmation of the Einstein-Podolsky-Rosen experiment, EPR experiment. So yes, as I said, if we have n qubits, then the state space has complex dimension not 2 times n, but 2 to the n, exponentially large as a consequence of this axiom. And this will be realized, this will lead to the qubit registers, right? A register of several qubits living in a very high dimensional complex state space. And the orthonormal basis for that is commonly denoted by, in this way, 0, 0, 0, 0, 0, 0, 1. And so they are numbered in binary. And you see they're 2 to the n binary numbers of n bits, right? So this corresponds to the dimension. And remember that this is a short form for Cartesian product of these unit vectors. Right, entanglement. That's one of the mysterious aspects of quantum mechanics that puzzle people. Yeah, it's very hard to grasp that because there's no classical counterpart to it. Our experience suggests very differently. And let's illustrate that with the case of 2 qubits. And here I'm going to change notation a little bit, not 0 and 1, but plus and minus. So we have a 2 particle. Each one has spin up or down, or X polarization and Y polarization, indicated here with a plus for the first particle, and plus or minus for the second particle. So we have 4 different combinations, unit vectors forming an orthonormal basis of this complex 4-dimensional Hilbert space. And Albert Einstein, who was always opposed to quantum mechanics, he said quantum mechanics is incomplete because the axioms only say that some eigenvalue will be the result of a measurement. Doesn't say which eigenvalue, only assigns probabilities. And Einstein famously has said, God doesn't throw dice. So a good physical theory should not involve any randomness, not allow for God's miraculous interaction. And he criticized quantum mechanics for that, as developed by Schrödinger and John von Neumann. And Einstein tried to refute quantum mechanics by constructing a thought experiment which would demonstrate the paradox of quantum mechanics. And this is the EPR, Einstein-Podolsky-Rosen thought experiment. Podolsky and Rosen are co-authors. Well, actually, Einstein was not the leading author in this paper. He developed the ideas together with Podolsky and Rosen. And I think it was Podolsky was technically the lead author. Yeah. Observe that here, the names in this publication are listed in alphabetical order, not in order of priority. This is something that still remains a tradition, for example, in computer science, to list names in alphabetical order without considering or expressing any priority among the authors. It's kind of all authors are considered equal in computer science, and I like that. I think other disciplines should follow that tradition of not ordering authors. But anyway, yeah, so but back to the EPR experiment. The EPR experiment considers a source which like the oven exhibit in, or silver atoms, but here it's the output of the oven. The source here is pairs of particles, and it's suppose it's designed in such a way that at every instant it exhibits a pair traveling in opposite direction, one in this direction, but in one is this direction, but they are created at the same time, and therefore they have a joint space. So this is a Cartesian product space, state space. And in this direction, there's a polarization filter, like the Stern-Gerlach inhomogeneous magnet. And here's another polarization filter, another Stern-Gerlach magnet. And then we measure the spin of this particle, and we measure the spin of this particle simultaneously. Now, let's suppose the output of this source is a pair of particles, one with spin up and the other with spin down. And then this pair is kind of split up and one particle travels in the one direction. We will in the next consider another case where the roles of the two particles are reversed. But an important hypothesis of this thought experiment is that this source only creates pairs of particles with opposite spin. So not plus plus and not minus minus, but only plus minus or minus plus. And this is easy to create with having an additional filter that kind of swallows all particle pairs when they have plus plus and swallows all particle pairs when they have minus minus, and only lets pass particle pairs with opposite spins. Now, the particle pair is emitted and split up, and one travels in this direction, the other travels in this direction, and then this particle will go up here, and this particle will go down here. It's one case. The other case is this particle pair. In this case, the particle will go down here, and this particle will go up here. And the paradox constructed by Einstein, Podolsky, and Rosen is that now performing a measurement, right here, this is a measurement on one particle reveals the polarization of the other particle, and even more, changes the state of this remote particle. Remember, one of the axioms was that performing a measurement affects the state. And if this is very far away, then performing a measurement here would instantaneously change the state of this particle, and with faster than the speed of light, right? Instantaneous with the state of here, this one. Performing a measurement here would result in a change of the state of this particle. And if this is like 20 kilometers, this experiment has actually been conducted at the Lake of Geneva, then according to quantum mechanics, this measurement changes the state over the distance of performing the measurement here, changes the state here over 20 kilometers distance instantaneously faster than light. And that's what Einstein saw as criticism, tried to refute quantum mechanics. Because performing a measurement, the result will be with a probability, and performing a measurement changes the state. But it turns out that this is actually what's happening. Only it's happening statistically with probability, not deterministically. And this leads us to the other kind of paradox of Schrödinger's cat. Maybe performing a measurement changes the state. And this thought experiment is put the cat into a box, and in this box also put in a radioactive material which may or may not exhibit a strong alpha particle that triggers a poison flake with a poison to be broken. And if it breaks, then Schrödinger's cat dies. If it doesn't break, then Schrödinger's cat lives. But as long as we don't look into the box, as long as we don't perform a measurement, we don't know. And in quantum mechanics, not only we don't know, but it's undetermined. Schrödinger's cat is in a mixed state, state between well, an entangled, no, not mixed, please delete that word, not a mixed state, but in a pure entangled state of both being alive and dead. And when we open the box and look and see that the cat has died because the radioactive decay has taken place, then the state collapses into either the dead or the alive state. This is a thought experiment, but this is not at all confusing. Well, yeah, it's designed to confuse you, but the reason for that is, yeah, I'm not going to go into that. It's a long discussion involving the Copenhagen interpretation versus the statistical interpretation of quantum mechanics. I'm not going to delve into that. Anyway, so the common refutation of Schrödinger's cat reproach is that these are macroscopic objects, and quantum mechanics only applies to microscopic objects like radioactive particles decaying, right? So cat is, of course, not just microscopic, but it's a system of like 10 to the 30 atoms, and therefore not subject to the description of quantum mechanics. Anyway, so let's move on and talk about quantum gates on one qubit. Remember, qubit, up or down, 0 or 1 in two-dimensional Hilbert space. And quantum gates are operating on qubits. We first discuss qubits, 1 qubits and quantum gates on 1 qubit. Next slide will be about quantum gates on qubit pairs on 2 qubits. And then we'll proceed to larger qubit registers and quantum gates operating in them. And our goal of this chapter 4 is to reach Shor's algorithm as a quantum circuit operating on n qubit simultaneously in order to factor large integers, n bit integers. So here we have such a qubit register with, let's say, 6 bit, but our gate here operates only on 1 on the first. So the first one, two-dimensional Hilbert space, up or down, 0, 1. And remember, according to axiom 5, the time evolution of any pure state is described by Schrödinger's equation. Instead of Schrödinger's equation, can also proceed to a semi-group, or actually a group perspective. And that means that quantum gates are unitary. So the evolution here is unitary. This is because of the complex unit here, I. That means the state at time t is the state at time 0 multiplied with a unitary operator. And unitary operators are reversible. So any quantum gate we're going to consider must be unitary and therefore must be reversible. And here are some simple examples of quantum gates on 1 qubit. So that's the so-called NOT gate. Pauli X gate, described by matrix, right? So we're two-dimensional complex Hilbert space, so a 2 times 2 complex matrix with complex entries. And this is a matrix, and you can verify easily that it transforms 0 into 1 and 1 into 0 with, remember the abbreviation. This is an abbreviation for 1, 0, 1, and this is an abbreviation for 1, 0, the pair in this two-dimensional space. So that's a classical gate, NOT gate, translated into the qubit setting of 1 qubit. Here's another example of a 1 qubit gate, Pauli's Z gate. So here the matrix is +1 and -1 here on the diagonal. So it translates 0 into +0, not changed, and it translates 1 into -1. Right? Remember, we're in a Hilbert space, so -1 is a new vector here. The third example we want to consider is the Pauli Y, which scales and switches, but with complex unity, -I times 1 and +I times 0. And but there's a fourth one we want to consider, and that's the phase changing gate. This gate only changes the phase, phase meaning scaling, multiplying with a complex number of magnitude 1. For the second case, maybe 1 vector. Okay, 0 vector is unchanged, 1 vector is multiplied with a phase change. And we use that actually when we discuss the circular polarized light, namely when the phase vector phi is equal to pi, or 180 degrees, right? Then this is just I according to Euler's identity. So this is a phase gate change. Phase changing gate can turn linearly polarized light into circular polarized light. So this is our 3 examples of quantum gates on 1 qubit. We can apply them to this qubit and leave the other qubits unchanged, meaning applying the identity operator to these qubits. Remember, the state space of this register is H, Hilbert space of 1 qubit raised to the tensor product. But we can describe an operator on a tensor product space by describing it on each individual qubit separately, like on this qubit. And on the other qubits, or we need to define the operation on the other qubits, and we can do that by describing it with a tensor product of the identity operator in this way. N minus 1 fold plus 1 fold. So that's an example of quantum gates on 1 qubit extended to all qubits. All I wanted to say today is about a recap of the axioms of quantum mechanics. And then we started talking about qubits and qubit registers and quantum gates operating on qubit registers, first operating on 1 qubit, operating on 2 qubits, and operating on n qubits. And next time we continue discussing quantum gates operating on n qubits, like the Hadamard gate, which we discussed today. And then we're going to discuss the discrete Fourier transform as a quantum Fourier transform. And then we will proceed to so-called phase estimation quantum circuit. And then we're already ready to discuss Shor's algorithm. So that's all for today. Thank you very much for your attention, and stay tuned for the next part on chapter 4, quantum computing, talking about quantum phase estimation circuit. Thank you very much, and goodbye.